We were discussing FDM or triple F, feast filament fabrication. Sometimes, as I mentioned, I use FDM, sometimes triple F. But we said that FDM is a trademark of Suttis company, but triple F, feast filament fabrication, is a name given by the ASTM, the standardization organization. So maybe it's better we use for most of the time triple F. So what are the limitations in phase deposition modeling? First of all, we have a limitation in terms of layer thickness. This is actually the minimum layer we can have. Below is almost not possible since we are extruding material. In order to maintain the integrity of material, you cannot have less than that number. Even maybe 60 micrometer is fine, but 50 and underneath is quite difficult and sometimes impossible. Another issue is that we cannot have sharp corners since we are using kind of a circular nozzle. If this is a top view, let's say, you cannot have such a sharper corner since we have a circular nozzle. This is moving over the, let's say, edge. And once it comes to here, comes to the corner, we will have a kind of a circle here. So that's why we say that sharp corners are not possible. You can have a kind of a smooth, let's say, fillet at these corners due to the shape of the nozzles we are using. Another thing about the products, their quality obviously depends on the nozzle type, the quality of your nozzle, whether you have any clocked material that is clocked, or the acceleration and deceleration characteristics of your used motors. For instance, this might be the S curves. So this part is actually if this is an speed versus time. So this is your acceleration characteristics. And at that point, starts acceleration. And during our motion on the table, your extruder is always accelerating and then going at a constant speed and then decelerating. But the thing is that these profiles, these motion, let's say, characteristics greatly affects your quality. Since you need to be careful about the amount of material extruded during these times. If you extrude too much material, then you will have such extra materials around. Your, let's say, bead width might be too much, and your accuracy will be decreased. Another important issue which is affecting the quality is the viscoelastic behavior of your material. And as you know, it changes with temperature. So we should have proper modeling and have a proper temperature control in the system. Otherwise, the quality again will be lowered. And this is somehow related to the previous things. The speed obviously depends, the fabrication speed depends on the feed rate, the amount of material we are extruding while we are going over the table. And the plotting speed is about the speed we are moving on the table, but feed rate is related about extrusion, extruded material. The rates, the amount of material actually we are extruding in unit time. And lastly, if you want to have more precise movements, then it's better you use lead screws instead of the belts and the stepper motors. But once you use servo motors and lead screws, then the accuracy will be much better. Now we'll start discussing another extension of material-based extrusion systems, and this is called bioextrusion. As the name implies, we are trying to extrude some biological things, biological materials, and again the fundamentals are the same. We need to have a kind of an extruder. We'll put our material in that chamber, and then with help of sometimes pressure or some chemical reactions will be performed, and we will be extruding these biological materials out of the nozzle. And for bioextrusion, we may be using some thermal, let's say, reactions, thermal processing, or some chemical reactions can also be utilized while doing the bioextrusion. But obviously, in order to retain the shape of the extruded material, again, solidification is quite important. After these biological materials are extruded, they should solidify as soon as possible and keep their shape as soon as possible. And why do you use bioextrusion? And the main idea is to actually fabricate scaffolds. The scaffolds are kind of actually mechanical structures for the cells. You will have such kind of, let's say, kind of grids, and obviously this is 3D. So that you have a kind of a 3D grid, and that will be the kind of an scaffold, and we use these scaffolds to actually grow some cells. And the ones having little, let's say, gaps between these grids is called as a kind of a scaffold with micropores. But if the gap between the grids is quite larger, then it's called a scaffold with macropores. And the advantage of macropores is that you will have the cell growth easily, since you will have more region for the cells to grow. It's preferred for that purpose. But if the adhesion of your cells on that scaffold is important, then it's better you use micropores, since the cells will not be able to fall down or go other places. With the help of these scaffolds having micropores, your cells can easily be stick to the scaffold. So here's then kind of a hydrogel, and the hydrogels are quite important, and in bioextrusion for most of the time, about 90% of the time, and we use hydrogels, and they, as you see again, we have 90% of water inside these hydrogels. So this is a nice advantage, since after the fabrication is over, once this water is evaporated, we will simply have the required material actually. Not the water. Water will be evaporated, and we will have the biological, let's say, scaffold. The remaining part will be biocompatible, and you can start growing cells inside these, let's say, regions of the scaffold. We may have some natural ones, natural hydrogels, and also synthetic ones. Depending on your application, you can find appropriate type of hydrogel for your problem. And we have some special type of printers which are using the same principles with the FDM or FFF, but obviously their extruder head is quite different. I will show you some examples, but let's have a look at some important regions. But I think not any item we haven't discussed. Obviously, if you want to use more biocompatible polymers, they are quite expensive, not as cheap as PLA or ABS materials. You need to pay more for these biocompatible materials. Another thing, you can even obtain non-Newtonian mixtures by preparing using proper amounts of materials. And sometimes, instead of just using a syringe or pump, people prefer to use screw feet like the Archimedean screw. They are used for bioextrusion. Now I will show you a company from Turkey, this Accelerated Biosystems. They are in Turkey. I will now share the window. If you have questions, feel free to ask. Yes, guys, this is a very simple bioextrusion system, and you can see that again they have 3 axes. This table is moving in Z direction, and then they have X and Y with the help of these stepper motors. some belt systems. And the thing is that please focus on this region in a moment. They have a bit complicated extruder. Now you see they have many, let's say, cables, tubes coming into the extruder. They have kind of a syringe here, and their nozzle is quite different. And again, they have some kind of fans sometimes, depending on the material. They may not even use it, or they may use some extra light sources. Again, it depends on the type of material they are using. And please have a look at here. There are about 6 or 7 tubes. Probably they have some biomaterials inside, and they are always pushing these materials into the mixing chamber. Now you'll see in a moment how they manufacture a scaffold, and you'll see this is a scaffold and very simple architecture. They will later use the scaffold to build actually cells for some tissues or other purposes. Probably they have a different mixture on this blue one. Now it's about to finish. Probably it might be a part of a bone. This is one of the common use areas. This is a scaffold, as you see, and we have quite macro pores, not micro, but we have macro pores. So we have more regions for the cells to grow. Let's see.
O plastik parçanın üzerine mi, yani biyomekanik parçanın üzerine mi sarıyor?
Yep.
Aa.
That is what actually these guys are doing usually. Or I may show you another one from the Envision Tech. This video is a bit older, but they are using the same principles. This is their type of printer. It's more actually, I think, complicated. They have some extra nozzles here, but the fundamentals are the same. Now I think in a moment you can see the macro pore here. They usually using a syringe and obviously pressure. So this is their scaffold. They are printing a kind of a jaw. So if you're interested, you can have a look at the details of these videos. Some other properties of the printer. So as you see, they have many extruder heads. And they have a cleaning region here. So these are examples for some scaffolds. It's a very special one, I guess, and probably they were printing a scaffold having micropores. So I think that's fine. Let me share this one. Yes. Any other questions, guys, about bioextrusion? Okay. You see some examples, some micropores. As you see, this is 0.5 millimeters or 500 micrometers. The gap here, the size of the pores. You may have different patterns. Another thing about bioextrusion is that they actually must have kind of continuous paths. If you have discontinuity, then it will be quite difficult to control the extrusion. So that's why they have such simpler paths. If you look at here, they have a kind of a zigzag path, and they don't stop the extrusion. They stop it once the layer is completed. So what are other, say, properties, issues about bio-extrusion of scaffold architectures? And the thing about the nozzles is that diameters are quite important, and depends on the type of material you are using. You may switch to a very small one or a larger one. Again, it depends on whether you are printing a small scaffold or a large one. So you should be careful on the nozzle diameter. And as I mentioned, sometimes they prefer to have macro porosity, sometimes micro. It depends on their purpose. And usually these days there are many papers, many research going on in this field, and their aim is to always find the optimum architecture so that they will have a better, let's say, bone or a tissue once they put some cells on these scaffolds. Now I will, from this point on, I will start discussing some special cases of extrusion-based systems. The contour crafting is this system actually. In contour crafting, we have a kind of, let's say, let me draw a side view. If you do extrusion, then we will have such barreling effect. Assume that these are layers. And if you use a kind of, let's say, special equipment or a scraping tool, then what you do at each layer, you do some scraping. So this part is removed, and the other part will be removed. And at the end, you have a perfect, let's say, extruded material. And this is done with the help of this scraping tool. And it is used to smooth our surfaces, obviously, and you can eliminate such staircase effect. But obviously, if you have an inclined surface, it's not possible. You can, in such inclined regions, what we are going to have, we will have such an maybe staircase, a perfect staircase. But if you don't use a scraping tool, that will be the staircase actually without using the scraping tool. But once you use it, then you'll have such a perfect, let's say, staircase. And with the help of the scraping tool or contour crafting, the layers might be thicker than the conventional approach. Another advantage of this method is that you can do the fabrication in a shorter time. And as you see in the next slide, people are using such methods to do some construction. Let me share it with you once again. So they are here actually mentioning about the conventional 3D printing. So they were inspired by this problem and then started using the same principles in construction.
The following one is the first concept of a house printer.
There are many other companies actually working on such 3D construction. If you're interested, you can search and see some other examples. Life side, as you see, house printer.
That's able to produce large settlements in a short period of time.
And as I mentioned, they are using a kind of a scraping tool to do the printing.
The y-axis, this is where the printing head is mounted.
So this is their y-axis, and they have x-axis here, and this is the printing head, obviously. Again, the fundamentals are very similar to the other extrusion-based systems.
Its lead press is extruded by the 4x nozzle. Therefore, it has a bigger moving range. The print head has 3 different openings.
This part is actually the scraping tool.
Here you can see a load-bearing wall.
Obviously, they need to have some infill patterns.
The nozzle can produce blockouts for the pipework or electricity. That's the point where the robotic arm comes into play. it grasps a little bit out of the
For top of the, let's say, windows, they use some special equipment. Otherwise, it's not possible since we need to use support structure. So in order to eliminate the use of support structure, they have such extra mechanical components. And then obviously they can easily switch to the second floor and do the same.
Concrete is most used rock.
Any questions, guys, about these systems, bio-extrusion or contour crafting? This is another example. It is called as carbon fiber printing. They have, again, used the same principles with the triple F, fixed filament fabrication, but this time they have filament of carbon fiber and another spool of, let's say, nylon or different materials. With the help of it, they were able to print more durable, more stronger, much stronger products. Now I will show you the fundamentals of their approach in a moment.
Very few manufacturing processes that can come close to this. It's just absolutely a breakthrough. You know, this is inventing something new. It's an incredible step forward to be able to 3D print on your desk a part that's as strong as metal. We invented this new machine.
So they are claiming that the printed parts are as strong as metals.
And it's also, we have a 3D printer that can print carbon fiber.
Yes, that's actually what they are doing. This gray material is probably nylon, and the black ones are carbon fiber. So they are actually using carbon fibers from the spool, and they are extruding it through the kind of a similar nozzle. But the thing is that they cannot easily stop and start the extrusion. And instead, what they do, they use a kind of a scissors and cut the carbon fiber material, and then switch to other materials, switch to the different regions.
Got long continuous strands of carbon in this new material that enables you to 3D print carbon parts. This is a significant advancement in material science. For the first time, you can 3D print a part that is as strong or even stronger than metal. Carbon fiber is used to make anything that's awesome. It's the lightest, strongest material in the world. What we've done is we've made it so that you can now start to take this kind of wonder material and build things out of it that are not as expensive. To actually design something in a moment and create it and put it to use is very, very powerful. So people have been trying to do this for at least 18 years. I thought it was great.
So this was their earliest one of the models, but now they have much better products. They even have the second, third version. If you're interested, you can again check their website. I think here they have some tests. You can see the carbon fiber underneath. I think you don't need to go into details. So if you are interested, as I said, you can have a look at the website of the company. We have another one, but again, similar. I'm not going to show this one. If you're interested, you can simply click. They are extruding ceramics. They have a kind of a special mixture here. With the help of pressure coming from this tube here, they extrude the material and have such kind of vases. So as you have seen in the previous slide, there are some printers actually specialized on ceramics. They need to have some paste of ceramic. So in such kind of printing, the preparation stage is quite complicated. You need to have proper amount of, let's say, aluminum or other different kinds of ceramics. Since in triple F, as you know, the material should be solidified after it's extruded from the nozzle. So this is the biggest challenge for the ceramics case. You need to maybe have some other chemical reactions after the part or the material is extruded. It's quite complicated. So with the help of it, you can print some complicated ceramic structures, which is not possible with other conventional approaches. But we don't have actually a commercial machine working properly. In the stereolithography chapter, we will see that by using stereolithography, they are trying to print some ceramics, but it's not that finalized. They are still doing experiments, try to finalize the parameters, but maybe in few years, we will have such printers capable of fabricating ceramic structures. Then I will briefly want to talk about some low-cost additive manufacturing systems or low-cost extrusion-based systems. The first one is RepRap. I think some of you may know. This is let's say, kind of a movement by the hobbies. For most of the guys are usually kind of hobbies, and they have come up with the idea that they should kind of establish a printer, and that printer should be capable of printing itself. And that's why it's called as self-replicating printer. Once you have that printer, by using some extra components like motors, some steel rods, you can print another printer. So we can say that it's the first general purpose self-replicating manufacturing machine. Then you can follow the rules of it and try to print another printer for you. There are such other websites, and these days it's not that complicated to construct a 3D printer on your own. By spending some few bucks on required equipment, you can try to construct a new 3D printer. These guys are mostly use open source, let's say, resources. Even the hardware, the design of the hardware are available. You can download and try to fabricate them elsewhere. The software, the firmware are all open source, so you don't need to pay a lot to construct the 3D printer for you. That's why we call these systems as low-cost extrusion-based systems, and this is one of the reasons why we have the democratization of manufacturing these days. If they didn't come up with such an idea, we wouldn't be able to democratize the manufacturing. And also we have some other extrusion-based systems. By using similar principles, we can print batteries, we can even print some actuators, or we can even print some electrical boards. So once you can actually extrude conductive inks, then it's not that difficult to print such PCBs, printed circuit boards.